Hey, so we're going to be looking at section 12.3, which is going to be talking about the antiderivative related to exponential and logarithmic functions. So I wanted to give you guys just a quick little cheat for when you're finding the antiderivative of something that has an e to it. So if you have the antiderivative of e to the k times x dx, where k is just some number, then the antiderivative is going to be 1 over k e to the kx plus c, where c is some constant. Okay, so that's the cheat. I'm going to show you both ways. I'm going to show you the long calculus way, and then we'll use the cheat way to make sure that our answer is correct. So here we have the antiderivative of 9e to the 3x dx. So what I notice is that this isn't just a plain old e to the x, it's an e to the 3x, which means I have e raised to some other function. So what I'm going to do is I'm going to let u equal 3x, and then when I take the derivative, I'm going to get du equals, well, the derivative of 3x is just 3 dx. Now what I'm going to do is I'm going to try to get the dx by itself, so I'm going to have 1/3 du equals dx. So I divided both sides by 3. Now what I'm going to do is I'm going to substitute all of that information to here. So I'm going to have the integral of 9 e to the, so I replace 3x with u, so that's going to be u, and I replace dx with that 1/3 du. So what that is going to become is that's going to become, well, 1/3 times 9 is going to be 3, and I can stick constants out in front. The antiderivative of e to the u du. So the antiderivative of e to the u is just e to the u plus some constant c. Now what I need to do before I'm done is I need to re-substitute in my original variable, which was x. So u equals 3x. So I'm going to have 3 e to the 3x plus c. Now I can check my answer by taking the derivative. So if I took the derivative of this, it would be 3 times e to the 3x times 3, remember by that chain rule, plus, and then the derivative of a constant is just 0. Notice if we had done the shortcut way, we would have got the same answer. So we would have had 9 times 1/3 e to the 3x plus c, which would have worked out to be the same thing. All right, now on the next one, I'm going to rewrite this a little bit. I'm going to bring the 12 out in front. And I'm going to rewrite this just because it's in the denominator. I can write it out of the denominator by giving it a negative exponent. Now I'm going to do the same thing I did before. I'm going to do some substitution. So I'm going to let u equal negative 7x. And then when I take the derivative, I'm going to get negative 7 dx. Now I'm going to go ahead and solve for dx since I don't have a negative 7 in front of my dx here. So that's going to be negative 1/7 du equals regular old dx. Now, when I resubstitute all of this information in, I'm going to have 12 times the antiderivative of e to the, remember, I said negative 7x equals u. And then I said dx is equal to negative 1/7 du. I'm going to go ahead and take my constants and move them out in front. So that's going to give me negative 12/7 times the integral of e to the u du. And the antiderivative e to the u is just e to the u. So I'm going to have negative 12 over 7 e to the negative 7x plus c. Again, if we had used our rule from above, we would have 12 times negative 1/7 e to the negative 7x plus c. So we would have got the same thing, just written a little bit differently. Now on these guys, we're not going to have the luxury of using that shortcut that we just used with e, so we have to be a little bit more finesse-y or careful. So here's the trick on this guy. So the trick on this is that we're going to look at which one has the higher exponent, and we're going to let that be our u. for when we substitute. So here, where we're taking the antiderivative, on the top we have 6x to the fifth, and on the bottom we have x to the 6 plus 10. So since that term, x to the 6 plus 10, has the larger exponent, we're going to let that be our u. Now when we take the derivative, we're going to have 6x to the fifth dx. So we don't have to do any fancy footwork now. All we have to do is a direct substitution. So this top part, 6x to the fifth dx, that's going to become du divided by, and that entire bottom part is going to be u. By the way, if it makes it easier for you, you can rewrite that as 1 over u du. Either way, what the antiderivative of 1 over u is very special. It's the natural log of u plus some constant c. And remember, we have to resubstitute in our original variable, so that's going to be the natural log of x to the 6 plus 10 plus c. Now, on this next one, again, I only have the bottom part, so I'm going to let that equal my u. So then what I'm going to have is I'm going to have du equals 7 dz. Now here's the issue. I don't have a 7 dz, I just have a dz, so I need to divide both sides by 7. And now I'm ready to do some substitutions. So this is going to become 1 over 7 du, because that's equal to z, divided by 7z minus 3, that's equal to u. I'm going to go ahead and pull that constant 1/7 out. So I'm going to have 1 over u du. Now the antiderivative of this is going to be the natural log of u with that 1/7 out in front, plus c, which would be 1/7 times the natural log of 7z minus 3 plus c. And remember, you can check your work on these guys by taking the derivative and making sure that it matches up with the original function.